So if we use the equations we developed in the last video, we should be able to calculate the principal stresses and the angle relative for the principal stresses uh, using those equations. So in this case, we're given the state of strain. All right, there's a small error in your book. The elastic modulus that's used in your book is very, very small, which is for aluminum. It's off by a factor of 10. So the actual modulus of aluminum is around 69 gigapascals, not megapascals. Alright, so in order for this to make any type of sense, the strain has to be reduced by a factor of 1,000 for E1, E2, and E3. So E1 would be equal to 20 microstrain, E2 would be equal to 5 microstrain, alright, and E3 would be equal to 10 microstrain. Alright, so if we plug in these values for E1 through E3 into the equations we developed on the last page, alright, so we're just going to use these equations that we have here down below on to solve for these individual values. Alright, so if we plug those in, right, we get our maximum stress, right, is going to be equal to our elastic modulus, so 69 times 10 to the 9 gigapascals. Alright, sorry, newtons per meter squared. Oops. Over 2. Alright, and then we're going to multiply that by the sum of E1 and E3, which is our 20 times 10 to the negative 6 plus 10 times 10 to the negative 6. We're going to divide that by our 1 minus the Poisson's ratio of aluminum, so 1 minus 0.33. Alright, we're going to add 1 over 1 plus the Poisson's ratio of 0.33. 4. Sorry, one last digit here. Alright, and then we're going to multiply that by the square root of E1 minus E3 squared. Alright, so E1 minus E3 squared. Alright, plus 2 times E2, oops, 2 times, sorry, so E1 minus E3 would be 20 minus 10, so that would be equal to 10 times 10 to the minus 6 squared. Alright, and then we would get 2 times E2, which would be 10 times 10 to the minus 6, minus the sum of E2, E1, and E3. So, and then all of this would be squared. So the sum of E1 and E3 would be 30 times 10 to the minus 6, and that would be that minus 20 times 10 to the minus 6 after we do the subtraction would be squared as well. So if we do all that math, what we end up getting for our maximum stress is we would get 2.13 megapascals. All right. We could repeat the process for the minimum shear stress. So the one thing I like to point out here in these equations is there's a lot of like terms. So the minimum shear stress is the same as the maximum shear stress, except for this one negative sign. The whole rest of the equation is exactly the same. Alright, so all we need to do would be to take the minus sign here, alright, and our minimum shear stress would be equal to 0.976 megapascals. All right, and then the last thing is the maximum shear stress, tau max. All right, it's the same equation actually as if you took just the right-hand term of our principal stress equation and we multiplied out the Young's modulus term into that part of the equation. So if you do the maximum shear stress equation, if you solve for the maximum stress, you can then, it should be very simple if you do each of these terms individually to calculate the minimum stress, the minimum normal stress, and the maximum shear stress. So if you do that, plug in that equation, all right, what you'll end up getting is you'll get tau max would be equal to 0.578 megapascals. All right. Now, the the angle of this relative to the x-axis would be equal to minus 31.7 degrees. All right. So what this means is that if we had our x-y coordinate system, all right, the first principal stress axis would be 31.7 degrees away from the x-axis going in the clockwise direction. Right? Right? And then the maximum shear stress is always 45 degrees away from, in terms of its direction, from the maximum maximum normal stress. All right. All right. All right. So that's how you would use the equations if you knew the strain within a strain gauge rosette that was offset by 45 degrees to determine the maximum and minimum stresses, principal stresses, as well as the maximum shear stress and its location.